In the last class, we were doing material symmetry, isn't it? So today is lecture 17. So you can recall that in the end, we had W of F equal to W of FQ, and that's due to material symmetry, which implies that phi of C is equal to phi of Q transpose CQ, and this is for all Q in symmetry group of material. And then we further said, if we talk of isotropy, then Q is the entire SO3, right? And in fact, we could also make it O3, because you remember we could insert one minus here and then another minus here, and so it became O3. It could also contain reflection. And so we then had to find out the invariance. So the next step was to get strain or the invariance of C. And it turns out for isotropy symmetry group, we have three which are IC, 2C, and 3C. So the energy will just depend on those invariants because it has to satisfy this relationship. So it can't depend on any arbitrary form of C. It has to depend on these invariants. And then the relationship can be arbitrary, just that it has to be function of invariance. To prove if a material has isotropy subgroup or isotropy symmetry group, in fact it is both ways. So it says a material has isotropy symmetry group if and only if phi of C is equal to some function phi hat of IC, 2C, 3C. See, you know this trick of if and only if? It means both ways. So you can, starting from symmetry, starting from the fact that it has isotropy symmetry group, you should be able to come here, or the other way also, starting from this energy form, you should be able to come back here. So you have to prove both ways. I will not, of course, do that proof here. So once you prove it, then only you can say that phi C is equal to phi hat IC 2C 3C. So you have to prove both ways basically. You know, one of the ways is easier. Which way is easier? Can you think of which of the ways is easier to prove? For example, can you show that indeed if C goes to Q transpose CQ, I think this we did already. So if C goes to Q transpose CQ, then IC 2C 3C remain unchanged. This we proved last time. So this establishes this part of the proof. So if it has symmetry group, that means C is changing in this way, then IC 2C 3C remain unchanged. So this statement is fine, that phi C is equal to some function phi hat of IC 2C 3C. But going the other way, so how to prove this? That's also not hard, but it's a bit tricky. Maybe why don't I make this assignment for third assignment problem 1? During a break you think about it. Problem 1 assignment 3. Okay. So basically you see we here. So what are the questions here? Once you identify what is the symmetry group, you have to find out what are invariants. For a transversely isotropic material, for example, think of a body which have, let us say, fiber engraved in it along some direction, which is A naught, suppose. So such a material will have one property in the direction of fiber and in the direction perpendicular to the fiber. In all directions perpendicular to the fiber, it will have another property. So it's a transversely isotropic material. And you have several such examples, fiber reinforced materials, composites, they are examples of transversely isotropic materials. So what will be the symmetry group for such material? Here is another problem. Problem 2 is, what are the invariants for transversely isotropic material? Okay, you don't have to prove it, just write down what are the invariants. You go to internet and find out. But I will modify this question slightly after I have gone through some lecture. Okay. So this is one of the problems that usually is tackled through material symmetry, finding out the invariance. So what does one do once you get invariant? Once you get an invariant, of course, then you can find out what will be the expression of stress. So you simply have to take the derivative of the energy with respect to deformation gradient, for example, to get first Piola-Kirchhoff stress tensor, right? So before we start talking about the expression of stress, let me also talk about different measures of stress. We have till now learned about two measures of stresses. One is Cauchy stress tensor and then first Piola-Kirchhoff stress tensor. But there are many more. So let us talk about them. Okay, so you remember we said W is a function of big F. Then we used objectivity to say that there is a function sigma perhaps, or I forgot what did I use. Yeah, I guess I use sigma. So then we said there's some sigma which is dependent on u, and that was due to material objectivity. And then symmetry, if it's an isotropy, but we could also say that this is same as phi as a function of c, isn't it? So I'm not using symmetry yet. It's M material objectivity which always holds. Or we could think of, let's say, some um, psi as a function of Green Lagrange strain tensor, which is E. So E is half of C minus identity. So this is all because of material objectivity. So this will hold for every material. Now, why don't I take its time derivative and see what I get? So do d by dt of the entire thing, d by dt of the entire thing. So you have del w over del f double contraction with f dot, isn't it? Is it fine with you guys? Similarly, you could write this as del sigma over del u double contraction with u dot, which is same as del phi over del c double contraction with c dot, which is same as del psi over del e double contraction with e dot. Okay, so this is in the form of rate of stored energy density, rate, power form of stored energy, because it is all w dot. And you see each of the expression have got two terms here. The first one is this one, and then the another one, the derivative of the kinematic quantity. So they are existing in pairs. So therefore they are also called energy conjugates. The pairs are called energy conjugates. And then this is, we all know it is first pk, right? First Piola Kirchhoff stress tensor, which is the conjugate of f dot, because it is appearing with a double contraction of f dot. So we say that first Piola Kirchhoff stress tensor, or which we also denote by p, isn't it? So that's the energy conjugate of f dot. This one has also got a name. Maybe I should use another color. This is called Biot stress, which is the conjugate of u dot. Okay, this one is called second Piola Kirchhoff stress tensor. And let us denote this by S. And this is the conjugate of Green Lagrange strain tensor, E dot. Can we relate each of these stress measures? We know how to relate first pk to Cauchy stress tensor. can we relate the other stress measures here? So answer is, of course, we can do it. So let us try to do that. So for example, think of this one, how to relate them. So it's going to be del W over del F double contraction F dot, and that's equal to del phi over del C double contraction C dot. And then you plug in the formula for C in terms of F. So it is F transpose into F whole dot. Okay, which is same as del phi over del C double contraction F dot transpose into F plus F transpose into F dot. Okay, then let us see what we can do. See, the idea is now to separate F dot from this expression, and so that we can then compare with this on the left hand side, on the leftmost expression. So it has two terms, as you can see. So we can say this is del phi over del C double contraction F dot transpose into F plus del phi over del C double contraction F transpose into F dot. Now, what do you think about del phi over del C? Is this going to be symmetric? See, phi is a scalar function depending on C, which is a symmetric tensor. So Cij is same as Cji. So del phi over del Cij must be equal to del phi over del Cji, isn't it? Therefore, this is actually a symmetric tensor. It's a symmetric tensor. Okay, now see, whenever we have double contraction, you remember, if you have A tensor product B, this is same as trace of AB transpose. You must be remembering it now.
Yes, sir.
Okay, so here also we can write this as trace of del phi over del C into F dot transpose into F whole transpose. So this becomes trace of del phi over del C into F transpose into F dot. Yes, into F dot. Okay, then we can.
Sir, I had a small question here.
Yes,
Sir, what do we mean by the fact that these are different measures of the strain tensor?
stress. Different measures of stress.
Yes, sir, different measures of stress tensor. Sir, what do we mean by that?
Right. It's because each of them are derivatives of energy with respect to some kinematic quantity. So therefore, it's like the conjugate of that kinematic quantity. And that's some kind of stress. So you are right, why do we call it stress? But in general, people call it, because if it's a derivative of some kinematic quantity, then we call it some form of stress. It's just,
Okay.
by definition, and we say it is some form of stress. And then you will see that since they are also related to each other, and we certainly know that del W by del F is a stress measure, right? Because we could relate it to Cauchy stress tensor. So, and since all of them are related, so therefore it makes sense to say that they are also some kind of a stress tensor. Okay. Now you see, you also know that trace of A is equal to trace of A transpose, isn't it? So here also we can say this is equal to, okay, let me continue this right here. So this is equal to, so this is this form. So this is trace of del phi by del C F transpose into F dot. And then I take the transpose of the thing inside the bracket, the argument of trace, and it will be the same. So it is trace of um, and yeah, so the transpose of the thing inside the bracket, which is del phi over del C F transpose F dot and the whole thing transpose. And that's then trace of F dot transpose into F into del phi over del C transpose, right? It just, the sequence has to simply reverse, and each of them have to be transposed. Now this is also same as trace of F into del phi over del C transpose into F dot transpose. How did this happen? Because I said that this is A and this thing is B. So trace of AB is same as trace of BA. Do you remember? That is also one of the things. So the other thing is trace of AB is equal to trace of BA. And then this is finally F del phi by del C, because del phi by del C is symmetric. Double contraction F dot from the definition of trace. So you see, I could do the manipulation at the tensor level itself. I didn't have to go back to indicial notation. But we could have also started directly with, we could have done this whole thing even with indicial notation. Okay, so that's just one of the term, and let us see what is going to happen to this term. So what do I do with that? Hmm. So of course, let me first write it in the form of trace. So this is trace of del phi over del C, and then the transpose of that thing, which is F dot transpose into F. Okay, which is same as, okay, this is easier. This is same as trace of F dot transpose into F into del phi by del C. Why is that so? What did I use in coming here? Um, so I have used this property where this thing here is B and this thing here is A. And finally, this is same as trace of F del phi by del C into F dot transpose. And what did I use? I again used the same property here. But then this is A and this thing is B. And this is then equal to F del phi by del C double contraction with F dot. And you see both are same. So it's just twice of it. So what we have proved is that del W by del F double contraction F dot, that's equal to 2 times F del phi by del C double contraction F dot. And since F dot can be arbitrary, this simply implies that del phi by del C is equal to half of del W by del F into, okay, it has to come in the front, so that's equal to F inverse into del W by del F. Okay, and if you substitute del W by del F in terms of sigma, the Cauchy stress tensor, then you see that it is half F inverse, and what is then del W by del F? It is, I guess, sigma into F inverse transpose into det F. Can someone help me? What is this?
Sir, bit of sigma F inverse transpose.
Okay, so it has to be multiplied with det F, okay? And you can see that this expression is indeed symmetric. You take the transpose, you get back the same thing. And this was also symmetric to begin with. Okay, likewise, can you think of what will be, how do I relate second pk? I mean this thing here. So if you do the business again, you get del W over del F double contraction F dot is equal to del psi over del E double contraction E dot, but E dot, you know that this is half of C dot, because E is half of C minus I, so it is same as half of C dot. But C dot we just found out. So this was, so if you compare these two, we had del phi by del C double contraction C dot, and that turned out to be F del phi del C, sorry, 2 times, yes, it was 2 times F del phi del C F dot. So what will be del psi by del E double contraction half of C dot? It will simply be F del psi by del E double contraction F dot. And then when you relate the two, you simply get that del psi by del E is equal to F inverse into del W by del F. And this is your second pk stress tensor. Okay. And there's one more remaining, obviously, you can see it, no? The del phi by del u biot stress. So I will leave this for you guys. What is the relation between biot stress and first pk stress tensor? So this, I guess, is problem 3. Okay, so once we, there is another stress measure, of course, which is, maybe let me just do that for completeness. That is simply Kirchhoff stress tensor. So we have first Piola Kirchhoff stress tensor, second Piola Kirchhoff stress tensor, and the third is just Kirchhoff stress tensor. So, we just learned that W dot is equal to del W over del F, double contraction F dot. Now let me write down del W over del F in terms of sigma. And then we know that this is det F into sigma into F inverse transpose, double contraction F dot. Okay, and then you can do that trace business to say that this is same as det F into sigma double contraction F dot F inverse. Now, do you recall what is F dot F inverse? This was your question in the minor examination.
Grade V.
Grad V, isn't it? Grad V. So this is also equal to det F into sigma double contraction gradient of V, but this grad is with respect to Eulerian, so small x. But then you also see that sigma is actually Cauchy stress tensor, which is symmetric. So when you double contract symmetric with a general stress tensor, only the symmetric part of here will contribute to the double contraction. So you could also write this as det F into sigma double contraction, the symmetric part of it. So I'll just say it is sim grad x v. And this has got a name. This entire thing is denoted by D, rate of deformation tensor. So, and this thing over here, that's called your Kirchhoff stress tensor. Let's say it is tau. So what we have figured out is that tau is equal to J into sigma. Very simple. Okay, and tau is the stress conjugate of D, the symmetric part of velocity gradient. Okay, so these are different forms of stress measures. Let's get back to where we were. We had the expression of phi for an isotropic material, and we said it is phi hat of IC2C3C. I mean, sorry, I didn't have the expression. I just had the functional form that phi hat depends on IC2C and 3C. So what will be then second pk s? So we know that second pk, so this is second pk. So I want to get the expression of second pk s. So s is, just look up what is s. This is your s, and also check the expression of this particular expression. When you take the derivative with respect to c, this is what you get. So can we say that s is simply half of del phi by del c? If you relate these two, del psi by del e is s, so s is half of del phi by del c, isn't it? Have I made some mistake somewhere? Um, yeah, I think, sorry, s is twice of del phi by del c, it is not half. So s is equal to twice of del phi by del c. And why I'm doing in terms of derivative with respect to c, because you see what we have here, the invariants are of c. Therefore, it is easier to take the derivative with respect to c. Whereas S is the derivative with respect to Green-Lagrange strain tensor. So anyway, so finally we have S equal to 2 times del phi by del C, which we can write as 2 times del phi hat over del IC into del IC over del C. See, chain rule. Plus del phi hat over del 2C into del 2C over del C. Okay, plus del phi hat over del 3c into del 3c over del c. Okay, now these quantities are something that you can derive because you know the expression of IC 2C 3C, and I guess you have also worked it out. No, what is del IC by del C? Can someone tell me? So IC is trace of C. So what is the derivative of trace of a matrix with respect to itself? So this we have worked out already. So this turns out to be identity. Del 2c by del c. What is this? Can someone tell me what is this? This was in your minor examination.
Half of trace c whole square plus uh, trace of c square.
No, that is 2c. But what is the derivative of 2c with respect to c?
Uh,
Anybody remembers? Can you please look back at your notes if you have it? And this last one you already had in your assignment. What did it turn out to be?
Sir, trace of C into I minus C transpose.
trace of C into I minus C. Okay, so this is, you're saying for this one?
Yes, sir. Yes, sir.
Okay, this is trace of C into I minus C transpose. Okay, thank you. And what about this last one? Anyone for the last one? This was in your assignment, no?
Determinant multiplied by gradient of V, I think.
Determinant multiplied by?
Gradient of V.
But sir, that was the time derivative of.
Yeah, that was the time derivative. This is not the same thing. And that was time derivative of J. This is 3C is of course 3C is actually J square. Did you guys not do what is the derivative of determinant of a matrix with respect to the matrix? Have you not done it yet? See, 3C is what? Determinant of C, and I want to take its derivative with respect to C. So derivative of determinant of a matrix with respect to the matrix. So we haven't done it, is it? Okay, let me work it out. So let us say A is the matrix, and I want D determinant of A, or let us say del determinant of A with respect to del A, with respect to A. So how do I work this out? So as I have told you, this is a derivative with respect to tensor. Let us first scalarize the derivative. So we will find out d by d epsilon of determinant of A plus epsilon times, let us say, h. And this will turn out to be something into double contraction h. And then this will be what we want, del of determinant of A with respect to A. Right, this is the formula that we have worked out in the class. So the first step is to get this one, no? So how do I do this? Okay, so maybe we will, so it's of course a trick. So I can write it as d by d epsilon into determinant of A into determinant of identity plus epsilon into A inverse H. Is that okay? See, determinant of two matrices is simply determinant of product of the two matrices. And when you take the product, you get back A plus epsilon H. Right? Please tell me if you're not able to follow. You simply take the product of the two tensors inside and you will get this thing here. Okay, but then when you do d by d epsilon, this acts as a constant, so it comes out. So you have det A into d by d epsilon of determinant of identity plus epsilon E inverse H. Now I'm going to use what is called Cayley-Hamilton theorem. Do you guys know what is Cayley-Hamilton theorem? Some
Yes,
of you
sir.
may have heard about it. It's a very nice theorem. So it says that the characteristic equation of a tensor of a matrix slash second order tensor is satisfied by the tensor itself. Two. Now, what is this characteristic equation? You know, say you have a matrix A or tensor A, and you want to find out the eigenvalue. So Ax equal to lambda x. Then you end up with determinant of A minus lambda times identity. Okay, and you have to set it equal to 0, and then you end up with a cubic polynomial, remember, which is minus lambda cube plus lambda square into IA, which is trace of A, minus lambda into 2A plus determinant of A, which is 3A. So these are the invariants, IA, 2A, 3A, and that's equal to 0. This is called the characteristic equation, solving which you get the eigenvalues. So that's the characteristic equation. And the Cayley-Hamilton theorem says you can replace lambda with the tensor A itself and still it will be satisfied. So that means wherever you have lambda, replace it by A, and then it becomes minus A cube plus A square into IA minus A into 2A plus 3A times identity equal to 0. Okay, so this is going to hold for any matrix A. Okay, but what we want to use is just the expression of determinant of something in terms of this thing over here. So let me write it down again. So determinant, what we know is the determinant of A minus lambda I. When it is expanded, it becomes minus lambda cube plus lambda square into IA minus lambda into 2A plus 3A, right? This is something which is going to always hold, where lambda need not be an eigenvalue. Determinant of A minus lambda I is equal to this expression, right? And if lambda is eigenvalue, then this is also equal to 0, but I'm not setting it equal to 0. Okay? Now you see what we wanted was determinant of identity plus epsilon A inverse into H. Isn't it? This is what we wanted. Correct? Now, if I compare the arguments, this green one and with this red one, if we set, so in going from green to red, from here to here, if you simply set lambda equal to 1, sorry, lambda equal to -1 and make A to epsilon times A inverse H. Won't I get the same thing inside, right? A minus lambda I can be made I plus A epsilon A inverse H when we use this thing. So when I substitute lambda equal to -1 and A equal to epsilon times A inverse H, I get identity plus epsilon A inverse H. So I should do the same thing even on the right hand side. Substitute lambda equal to -1 and A to be epsilon times A inverse H. So when you set lambda equal to -1, this becomes +1. Lambda equal to -1, this is again +1. But now it is I of not A, but epsilon times A inverse H. Okay. Then coming to the third term, lambda equal to -1, and you get plus 2A. So this is 2 epsilon times A inverse H plus 3A, but A has to be epsilon times A inverse H. So is this fine to all of you?
Yes, sir.
Okay, now you see this
So,
1 epsilon A inverse H. Yes, you have
sir,
some question.
can we just take epsilon outside the determinant, and lambda becomes 1 by epsilon? Then
But how do I take
just be,
epsilon outside? How do I take epsilon outside determinant?
uh,
Because it is identity plus epsilon, no? How can I take epsilon outside?
so it will be epsilon times determinant into 1 by epsilon identity plus
But
A
still,
inverse.
you will still have 1 by epsilon, no?
Yeah, then we'll have to put 1 by epsilon in place of lambda.
Right. So
So,
I don't know how we can use that.
okay,
Maybe that
okay.
can also be useful, but let us try the way I'm doing. So this is now again equal to 1 plus, you see, what is I of a matrix? Is the trace, no? So you have to get trace of epsilon A inverse H. Now 2 of a matrix is that expression, but isn't that quadratic in the expression? Can I say that this is epsilon square into 2 of A inverse H? You just have to look at the expression of 2. Similarly for the 3, since it's a determinant and each of the entries are multiplied with epsilon, it is simply epsilon cube into 3 A inverse H. Will you agree with me? And then here I could take the epsilon outside and it becomes epsilon times trace of this thing.
We took the
Is that okay?
epsilon is common measure
Where?
from the matrix, a second variant of inverse A inverse H. That's why we write it epsilon square. And the third term also
Yeah, and the third term it is epsilon cube
epsilon cube. Like
because
we
it's a
use
determinant. So each of the, so you have 3 multiples for each
yes,
entry in, when you expand the determinant of a matrix, you have each term is a product of 3 components. And here each of the components are multiplied by epsilon, so you get epsilon cube. Okay, so, and you see what we wanted was d by d epsilon of determinant of I plus epsilon A inverse H at epsilon equal to 0. Now you see it is quite easy to do it now, no? So when you do it, you simply get trace of A inverse H, right? because others are, you have to finally set epsilon equal to 0. This epsilon square will become 2 epsilon, but then set epsilon equal to 0. This goes away. Epsilon cube will become 3 epsilon square, and you set epsilon equal to 0, that also goes away. So this is the only term remaining, and which you can also write as A inverse transpose double contraction H. Is that okay? Can you do that? See, this is trace, so it is same as its transpose, so it is trace of H transpose into A inverse transpose, which is same as trace of A inverse transpose into H transpose, and which is finally this number. Okay, so what we have proved, so you see, using this nice trick, we are able to find, so we have to, by the way, set it at epsilon equal to 0. So this becomes determinant of A into A inverse transpose double contraction H. Okay, so you can see that this thing over here is determinant of A into A inverse transpose. Okay, so finally this is then 3C into C inverse transpose. Now look at the entire thing here. This is the first derivative of phi hat with respect to IC. This will still depend on all IC 2C 3C. It's some function. Similarly, this will also depend on all IC 2C 3C. And this will also depend on all IC 2C 3C. And here, this thing is also your IC. So when you club all the things together, what do you get? You can say that second Piola-Kirchhoff S is some phi 1, which is a function of IC 2C 3C into identity plus some phi 2. Well, maybe I'll say it as phi naught, and I'll tell you why I say phi naught. And this as phi 1, which is also a function of IC 2C 3C into C plus phi inverse, which is a function of IC 2C 3C into C inverse. Can I write this? You see, I have simply clubbed the things together. You come back here. See, this is identity, and from here also you are getting IC into identity. So when you club the entire thing related to identity, it is 2 times del phi hat by del IC plus IC, and that's also 2 times of it. Yes, 2 times of it into identity. And this thing inside the bracket, this I have called as phi naught below. Okay, likewise you can see the coefficient of C. So here is your C trans, which is same as C. The coefficient of C is minus of 2 times del phi hat by del 2C, which I am calling at phi 1 below. And similarly, the coefficient of C inverse I am calling as phi minus 1 below. Okay, and that's why this is phi naught, because this is c to the power 0, that's why it is phi naught. This is c to the power 1, that's why it is phi 1. This is c to the power minus 1, that's why it is phi minus 1. Okay, is this clear to all of you? So basically we have been able to find out the expression of second pK for isotropic material in terms of I, C1 and C inverse. And then you can use Cayley-Hamilton theorem. That's what I wanted to do, but I just confused you guys. Look at this thing here. The idea is, can I replace this C inverse in terms of C and C square? That way it would be nice, no? You don't have to work with C inverse then. So answer is yes. Multiply this expression in the pink box with A inverse on both the sides, and you see what you get. When you multiply by A inverse, what are you getting? So you get minus A square plus A into IA minus identity into 2A plus 3A into A inverse is equal to 0, right? So this allows us to write down A inverse in terms of A square, then A and identity, isn't it? So you can substitute that thing in this expression, in this thing here for C inverse. And finally, you can write that S is equal to some phi naught hat of IC, 2C, 3C into identity plus some phi 1 hat of IC, 2C, 3C into C plus some phi 2 hat of IC, 2C, 3C into C square. Okay, are you guys with me? So this is the expression for second Piola-Kirchhoff stress tensor. For isotropic materials. Are you guys there?
Yes, sir.
Okay, very good.
Yes, sir.
Now, what is interesting to see here is that the eigenvector of C and eigenvector of S will be the same for isotropic. From this expression, you can tell that eigenvectors of C and S are same. Can you see it? See, eigenvector of C and C square are same, and that can also be the eigenvector of identity, because anything is an eigenvector of identity. So the whole thing in the right hand side has the eigenvector same as that of C, and therefore on the left hand side also it will have the same as C as the eigenvector. Is that I hope it is not confusing to you. Let me just do it again. So let us say, let V be eigenvector of C with mu as the eigenvalue. Then what will be S times V? So you get to that expression, it is simply phi naught hat into V plus phi 1 hat into CV, which is mu times V, plus phi 2 hat into C square V, which is mu square into V. And that's simply phi naught hat plus phi 1 hat mu plus phi 2 hat mu square into V. So this tells us that V is also the eigenvector of S. Okay? So this is what I wanted to say, that eigenvectors of C and S are the same. Can we find out what will be the expression for sigma Cauchy stress for isotropic material? So of course we can find out. So sigma, we know that this is same as is that 1 by determinant of f? So I'm again, yeah, I think it is 1 by det f into p into f transpose. Is that right? And we also found out the relationship between P and S, no? So P and S are related. We have to go back. So del W, del F, and S. So here it is. So P is equal to F into S. So from here, P is equal to F into S. So we get back. So this becomes 1 by det F into F into S into F transpose. And then you plug in the expression for S from above and see what you get. 1 by det F is, by the way, square root of 3c. So it is 1 over square root of 3c into phi naught hat into FF transpose, which is B, plus phi 1 hat into F into C into F transpose, F into C into F transpose, plus phi 2 hat into F into C square into F transpose. Now C is F transpose F, right? C is F transpose F. So this thing is then F into F transpose into F transpose. Sorry. And do you recall what is FF transpose? So FF transpose is B, no? Left Cauchy
sir.
green tensor. So this becomes finally 1 over square root of 3c into phi naught hat of B plus phi 1 hat of B square plus phi 2 hat, and this will be, I guess, B cube. Yes, this will be B cube. So from here you see that sigma and B share the same eigenvectors. Okay, so you see we are able to finally write down expression of S and sigma for non-linear isotropic material. See, it is not linear isotropic, it is non-linear isotropic material. And as I told you, I am going to modify assignment 2. Let me go up. And problem 2. Yeah, so what are the invariants for transversely isotropic materials? So this you can find out from internet. And furthermore, find expression of S for such materials. So you'll have to take the derivative of those invariants with respect to C to get expression of S. So here you did the derivative of IC, 2C, 3C. There are extra invariants for transversely isotropic material, and you have to take their derivatives also to get expression of S. Okay, do you recall from your second year undergraduate course, undergraduate solid mechanics, what was the expression for sigma for isotropic material? Do you recall? So sigma, we wrote it as lambda times trace of epsilon into identity plus 2 mu into epsilon. Can you recall this? And we also know that isotropic material has just two material constants. This is something certainly you would be knowing, no? Two material constants.
So two independent material constants, yes, sir.
Two independent material constants, yes. Independent. But how many constants do you see here? The expression for sigma, how many constants are there? Can you figure out?
Sir, 3, sir.
Why 3?
Sir, phi naught, phi 1, and phi 2. I think so.
But they are not constants, they are functions. They are functions of IC, 2C, and 3C.
Oh,
Right?
yes, sir.
So they are not functions. So they are not constants. So each of the function, see for example, phi naught hat. This is phi naught hat of IC, 2C, 3C. It could be, for example, A times IC plus B times 2C plus C times 3C. And then it has three constants ABC. And if you think it has more terms, so it's a function, it has infinite constants actually. Right? Same thing goes for phi 1 hat and phi 2 hat also. So what is the problem then? Why are we getting two different results here? Any idea?
There will be some relation between the constants.
No, there is no relation. Your phi, see this expression, phi naught, phi 1 and phi 2, they are general. They can be anything and still it will correspond to some material. You can choose it to be anything and you will not violate any of the laws. I think you have
Sir,
to answer this question. What
sir,
is
I
the
think,
problem here? Yes.
sir, this is for linear material, sir. Non-linear material. This expression is for, and there we have derived for.
Very good. That is very, very true. So this thing here is for linear stress-strain relation, because that's what we do in undergraduate course. So when we say two constants, it is only when you have linearly isotropic material, linearly isotropic, whereas this is non-linearly isotropic, general, most general. And it can have infinite constants. Okay. Now, so here is the last problem that I'll give you, and it is really a tough problem. Problem 4. Write down the expression of S in terms of E. You see, if you go up, you have the expression of S in terms of C. So you simply have to substitute C in terms of E. And linearize it further in E and show that it will only have two independent constants. If it has to be linear in E, it will have two independent constants only. Okay, so this is your problem 4.
Sir, so what exactly happens to the other constants when we take this linear assumption from there?
You work it out and see what is happening. So you already have the nonlinear expression. Try to linearize it using Taylor's expansion. You know, you have a nonlinear, you have just a function. Do the Taylor's expansion of the function in terms of E. All the functions. So you have phi in terms of IC, 2C, 3C. So you'll have to also linearize them in terms of E. Everything has to be written in terms of E, and just keep the linear term and forget about all the higher order terms. And when you club all the linear terms together, you have to show that that final expression has got only two constants. Okay? So with this, I'm going to close the lecture for today, and you're free to ask me question.
Sir, hello sir.
Yes.
सर सर पहले जब आपने सर डिटर्मिनेंट ऑफ ए माइनस लैम्डा ए को कंपेयर किया था आई प्लस एप्सिलन ए इनवर्स एस से, तो वहाँ
हाँ
पे
हाँ
लैम्डा इज इक्वल टू -1 हमने लिया था, और वहाँ पे आपने कहा था कि हम इसे कैली हैमिल्टन से मतलब कंपेयर नहीं कर रहे, एट मीन जीरो नहीं ले रहे यहाँ पे, इसलिए हम लैम्डा कुछ भी ले सकते हैं।
करेक्ट करेक्ट।
लेकिन सर बाद में जब हम सी इनवर्स को मतलब एलिमिनेट करने के लिए हमने कैली हैमिल्टन का यूज किया, और वहां पे हमने जीरो लेकर ही उसे यहाँ पे पुट किया, तब जाकर वो सी स्क्वायर के टर्म में आया। तो
नहीं तो ये
सर
तो
ये
हाँ, तो देखो ये कैले हैमिल्टन थ्योरम है जहां पे जो बोलता है कि लैम्डा को हम लोग ए से रिप्लेस कर सकते हैं।
यस
तो
सर,
so this expression is going to hold for any a, for any matrix a, this expression is going to hold। इसमें देखो आइगन वैल्यूज इसमें है ही नहीं अब। सो अगर ये एक्सप्रेशन रहे तो इट विल ऑलवेज बी इक्वल टू जीरो। दैट्स व्हाट कैले हैमिल्टन थ्योरम सेज।
सर बट रिलेशन तो हम लैम्डा -1 लेकर ही ना लेकर आए हैं लास्टली जो।
नहीं ये वाला कहाँ, ये वाला तो
ये
इसमें
नहीं
कहाँ
सर,
डाला है।
ये सर जो सी के टर्म में हमने निकाला है सर।
नहीं देखो, ये जो यहाँ पे लैम्डा -1 किया था वो तो बस इसके लिए था, ये डेरिवेटिव निकालने के लिए।
यस सर।
उसके बाद कहीं हम लोग लैम्डा -1 नहीं ले रहे हैं, उसके बाद हम लोग जनरल जो डेरिवेशन है वो कर रहे हैं।
ओके सर, आ गया।
Any more question?
Sir, ये phi, how do we calculate phi from? How do we find the function phi from the invariants? Like how? What is
नहीं,
the?
हाँ, that we can't find. We just know that it is a function of invariant. अब ये कैसा फंक्शन है, लीनियर है, लॉगरिथमिक है, साइन है, कोसाइन है, वो हम लोग मैकेनिक्स से नहीं निकाल सकते हैं, उसके लिए एक्सपेरिमेंट करना पड़ेगा। यस, बट स्टिल देखो हम लोग काफी हद तक निकाल दिया ना।
हाँ,
हमारे पास एक जनरल W था, पता नहीं था वो किस तरह से F पर डिपेंड करेगा, लेकिन यूजिंग द कॉन्सेप्ट ऑफ ऑब्जेक्टिविटी एंड सिमेट्री वी हैव फाइनली बॉइल्ड डाउन टू दिस एक्सप्रेशन। So it's a lot of simplification. But अभी भी पूरा नहीं निकला है। You can't avoid experiments.
सर यहाँ पे फाई नॉट, फाई 1 और फाई -1 जो है ये यहाँ पे हमें इनफाइनाइट कॉन्स्टेंट्स दे रहा है, राइट सर?
हाँ,
सर लेकिन अंडरग्रेड में जब हमने पढ़ा था सर, तो वहाँ पे 81 कॉन्स्टेंट्स आते थे। तो सर क्या वो लीनियर इलास्टिक के लिए सिर्फ वो 81 कॉन्स्टेंट थे? मतलब वहाँ पे सिर्फ हम नॉन लीनियर को कंसिडर नहीं करते?
वो जो 81 था, इट वाज फॉर लीनियर स्ट्रेस स्ट्रेन रिलेशन। वहां पर हम लोगों ने कभी भी नॉन लीनियरिटी की बात ही नहीं की।
अच्छा, दैट
स्ट्रेस
मीन्स
में
वहाँ पे, बट सर वहाँ पे हमें जनरल मटेरियल के लिए बोला जाता था कि ये जनरल मटेरियल के लिए 81 कॉन्स्टेंट्स होते हैं।
81 नहीं होता है, वो फाइनली आई थिंक 21 बन जाता है ना, क्योंकि स्ट्रेस
हाँ, यस
सिमेट्रिक
सर।
होता है, स्ट्रेन भी
हाँ,
सिमेट्रिक होता है, तो मेजर सिमेट्री माइनर सिमेट्री सब यूज करके जनरल एंड आइसोट्रोपिक मटेरियल के लिए अगर लीनियर स्ट्रेस स्ट्रेन
21,
रिलेशन है तो 21 कांस्टेंट्स होते हैं।
यस
तो
सर।
वो भी लीनियर के लिए था ना,
अच्छा,
यहाँ तो हम लोग नॉन लीनियर की बात कर रहे हैं।
ओके सर।
I hope that you guys are able to follow the lecture. These are quite difficult topics. कहीं भी बुक में जाओगे पढ़ने के लिए तो बहुत मुश्किल होगा, क्योंकि वो लोग ऐसा नोटेशन यूज करते हैं कि देख के ही डर लग जाता है। So but it is important to understand these topics.
Excuse me, sir.
हाँ,
Sir, एक रिक्वेस्ट था कि can you please suggest us some references where we can know more about the double contraction thing, because I'm not so much familiar about the double contraction mathematics.
familiar about what?
Double contraction.
अच्छा, डबल कॉन्ट्रैक्शन। तो डबल कॉन्ट्रैक्शन तो सिंपली है कि अगर ए डबल कॉन्ट्रैक्शन बी है तो वो ए आई जे बी आई जे है। हर कंपोनेंट को दूसरे कंपोनेंट से, कॉरेस्पॉन्डिंग कंपोनेंट से मल्टीप्लाई करके ऐड कर देना है। सिंगल कॉन्ट्रैक्शन अगर डॉट प्रोडक्ट है उसको सिंगल कॉन्ट्रैक्शन बोलते हैं, और यहाँ डबल कॉन्ट्रैक्शन है क्योंकि दो इंडिसेस कॉन्ट्रैक्ट हो रहे हैं। इससे और ज्यादा क्या जानोगे?
Yes, sir.
राइट, बाकी तो प्रॉब्लम जो आएगा उसमें यूज करना रहेगा उसको।
so
हाँ,
सर ये इनवेरिएंट्स तब पिक्चर में आए ना जब हमें पता चला कि जो सी है वो क्यू के साथ चेंज नहीं हो रहा है इस पर्टिकुलर सिमेट्री को।
करेक्ट, करेक्ट। No, not C. The energy is not changing.
एनर्जी इज नॉट चेंजिंग विद
C
सी।
to change here. C is changing to Q transpose CQ.
हाँ,
But
with
energy is still not changing. तो फिर तो हमको इन्वेरिएंट निकालना पड़ेगा कि क्या इन्वेरिएंट्स हैं जिस पे एनर्जी डिपेंड करेगा।
Okay, and those invariants are based on कि rotations कौन सी apply हो रही है, किन
Exactly.
rotation पे
Yes.
ये change होगा.
Yes. 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 Very true. हाँ.
So इसमें हमें तीन ही invariants हमें मिले.
हाँ.
ज्यादा भी हो सकते थे क्या? हमें कैसे पता कि तीन पे ही?
इसमें तीन. Yes. Exactly. वही तो उसी का मैंने प्रूफ बोला ना, तुम लोगों को करना है कि तीन ही क्यों हुआ.
ठीक है.
There are only two independent invariants. Invariants तो और भी है, जैसे कि आइगन वैल्यूज हैं, बट वी वांट जस्ट इंडिपेंडेंट इनवेरिएंट, तो सिर्फ तीन ही इंडिपेंडेंट इनवेरिएंट हैं.
ओके.
ओके, फिर देन गुड लक, एंजॉय द ब्रेक. ठीक है. ऑल्दो अभी तो कुछ करने का है नहीं, घर पे ही रहना है, बाहर तो जा नहीं सकते हो, फिर भी छुट्टी का मजा लो.
थैंक यू सर.
ओके, बाय बाय टू एवरीवन.